Hi, this is a comprehensive example from Beer Johnson's book, and which is a good example in a conceptual understanding of stresses, includes normal stress, single shear stress, double shear stress, and as well as a bearing stress in a frame. So if we do have this frame, which includes of a boom AB and a rod BC, which is connected with pin A, B, C, and pin A and C are connected to a fixed support, and pin at B dragged down by a 30 kN force downward. The dimension of boom and the diameter of rod BC are provided, and we need to calculate the reactions at A and C. At the same time, diameter of each pins, including A, B, C, are provided to be 25 millimeters. So to approach this kind of problem, the very first step is to draw a clear free body diagrams of forces, and as soon as you have that, by summation of moment about, for example, point C, you can calculate AX equal to 40k, and summation of forces in X direction gives you CX, and summation of forces at Y direction gives you an equation which includes AY and CY, and summation of them is 30kn. If you make another moment about point B, it just ends up to be AY equal to 0. As soon as you have AY 0, CY is a positive 30 kilonewtons. So far we had all the forces. AX is known, CX is known, CY is known, and this is a pictorial representation of the forces. And based on sine law, if we just create this triangle and including FAB, FBC, and 30kn, which is provided in the problem statement, you can easily say FAB over 4 is equal to FBC over 5 and is equal to 30 over 3. It simply gives you the numeric value of both unknown of a force at AB and force at BC. As you can see in this figure, it just gives you shows the AB is a compression member and BC is a tensile member due to the direction of forces which we just calculate. If you want to go a step farther, for example, here, and know what are after knowing the forces, now we just want to know what are the stresses, including normal stress, shearing stress, bearing stresses in either the links and the joints. So if you look at here, this figure just shows the pin C is at single shear, pin B is in a double shear condition, and pin A is also in double shear. So A is in a double shear, B also is in a double shear, and C is in single shear condition. To calculate normal stresses in boom AB and also rod, so for the links, first go for them. So FBC is 50 in tension, positive, and the area of BC is pi d squared over 4. If you replace the numeric value, gives you the cross-sectional area of the rod in square meters, and sigma BC is nothing but force over the cross-sectional area, which is positive 159 megapascal. However, the flat part of the rod is also under tension, and it just goes for the narrowest section, so we do need to go with net cross-sectional area. In doing that, this is the thickness of the plate, which is the diameter of the rod, and just 40, which is this part, minus 25, which is the diameter of the pin itself, and that gives you the area for that part. And sigma bc is p over area, but area this time is net area, and it just gives you 167 megapascal, again in tension. And that's, be careful, that's average stress. Now look at the beam, look at the boom AB, and that's a compressional force, that's negative stands for that, and that's 40 kN, 40 10 cube newtons over the cross-sectional area of the boom, and gives you a negative stress of 26.7 megapascal. Now let's see how about the shearing stresses in joints or connection. So if you can see here, there is a tensile force pulling the pin at C, which is in a single shear. If you cut the beam with a cross sectional of DD prime, it just gives you the visual representation of what happens there. The area of the pin C is pi r square, and that's the area, and average shear in pin C is the tensile force of 50 kN over the cross-sectional area, and that's 102 megapascal. The story at pin A, again shear, average shear in pin A is also stands in a double shear, so P over A, each of those part is handling a half of the force, so 20 over the cross-sectional area gives you almost 41 megapascal in shear. Let's have a closer look at pin at B. So pin at B is can be separated or divided into 5 parts upon the forces acting on that from boom, rod, and bracket itself. So due to the symmetry of the problem, you can consider half of the problem, so easily P at H is equal to P at G. So if you just cut it to half, it just gives you, go with the half of the forces, so 50 over to 25, and average shear P force at G over the area of the pin, it gives you 50.9 megapascal. If we go for bearing stresses, for example at A in boom AB, it just gives, AB goes by a thickness of 30 millimeters and a diameter of 25. So sigma B is 40 kilonewton over 30 millimeters times 25 millimeters, and that's 53.3 megapascal. Likewise, bearing stress in bracket A at A is which goes by a thickness of 2y of 25 times, which is 50, and the diameter of 25, and sigma B is nothing but forces over T times D, which is 50 times 25. And that's all for this exam. Thank you.